Quantum teleportation is one of the most fascinating and misunderstood concepts in quantum physics. Despite what science fiction often suggests, quantum teleportation does not involve instantly transporting people or objects from one place to another. Instead, it is a real and experimentally verified process that allows the state of a quantum particle to be transmitted from one location to another using the strange principles of quantum mechanics. In this video, we will explain quantum teleportation clearly, step by step, and explore why it is important for quantum technology. At the heart of quantum teleportation is quantum entanglement. Entanglement is a phenomenon where two particles become linked in such a way that the state of one immediately correlates with the state of the other, no matter how far apart they are. This does not mean information travels faster than light, but it does allow correlations that classical systems cannot achieve. Entanglement is the key resource that makes quantum teleportation possible. To perform quantum teleportation, three main ingredients are needed: the particle whose state we want to teleport, a pair of entangled particles shared between the sender and the receiver, and a classical communication channel to transmit measurement results. It is the combination of entanglement and classical communication that enables the process. The process begins with the sender performing a special measurement on the particle to be teleported and their half of the entangled pair. This measurement, called a Bell state measurement, entangles the particle with the sender's entangled particle and generates two classical bits of information. Crucially, the original particle's quantum state is destroyed during this measurement. This is consistent with the no-cloning theorem, which states that an unknown quantum state cannot be copied. Next, the sender transmits the two classical bits to the receiver using a conventional communication method, such as a phone line, optical fiber, or radio signal. This step is essential because the receiver cannot reconstruct the quantum state without knowing the measurement outcome. Importantly, this ensures that no information travels faster than light. Preserving the principles of relativity, once the receiver has the two classical bits, they perform a specific quantum operation on their half of the entangled pair. Depending on the measurement results, these operations transform the receiver's particle into an exact replica of the original particle's state. In other words, the quantum information has been successfully teleported from the sender to the receiver. The original particle no longer retains its state, and the teleportation process is complete. Quantum teleportation has been demonstrated in laboratories using photons, atoms, and ions. Photons are especially useful because they can travel long distances through optical fibers or even through free space. Experiments have successfully teleported quantum states over kilometers, showing that the principles work not just in theory but in practical setups. It is important to note what quantum teleportation cannot do. It cannot transport matter, people, or large objects. The process only transfers the information that defines a quantum state, not the physical particle itself. In principle, the state could be used to reproduce a particle elsewhere, but this is not the same as moving matter instantly. Quantum teleportation is significant because it provides a foundation for quantum communication and quantum networks. Entanglement-based teleportation allows the secure transfer of quantum information over long distances. This could lead to unbreakable encryption methods and global quantum internet systems, where information is transmitted safely using the laws of physics rather than relying on classical security measures. Another application is in quantum computing. Teleportation can move quantum states between different parts of a quantum processor without physically moving qubits. This helps reduce errors and increases flexibility in large-scale quantum circuits. Teleportation also plays a role in advanced error correction and distributed quantum computing, where multiple processors work together on a single quantum problem. The process also highlights some of the most counterintuitive aspects of quantum mechanics. The fact that a quantum state can be transmitted without moving the particle, that entanglement can link particles over long distances, and that measurement both destroys and enables state transfer, all challenge our classical intuition about how information and matter behave. In simple terms, Quantum teleportation is a way to transfer the exact state of a quantum particle from one place to another using entanglement and classical communication. The particle itself does not travel, only the quantum information is transmitted, preserving the no-cloning rule and the speed of light limit. Quantum teleportation demonstrates the power and weirdness of quantum mechanics in a tangible way. It is a stepping stone toward new technologies in secure communication, advanced computation, and distributed quantum systems. While it will not create Star Trek-style teleportation devices, it is a revolutionary tool in the emerging quantum era. Understanding quantum teleportation helps us see how information in the quantum world behaves differently from anything in classical physics. It shows that quantum mechanics is not just strange theory, it is a practical framework that allows us to manipulate and transmit information in ways that were once thought impossible.